Welcome back to the dynamic programming chapter. This is a chapter about programming paradigms. This is the last programming paradigm, and we continue after having introduced dynamic programming in previous sections and introduced the classical dynamic programming examples. We will see now one of the non-classical examples of dynamic programming. So how to add is a problem that is not classical. Not classical means what? It means you don't memorize the solution. You have to think about an original formulation of the DP states and transitions because the other you know them already. So we saw here that for each of the 6 classical problems we studied previously, you know what is the state, what is the space, what is the transition, and what is the time. So here you have to think about all of these DP terms. What is the state? How many parameters? You must choose the state to be the states to be different, to be distinct. What is the space? It means how many states, how many distinct states do we have? Because after all, DP is a tabulation, so you have to know is it possible to use the space, and you have to deduce the transition between the states. What are the trivial states? What is the transition between the states? And the time, which constitutes the complexity to solve one state, and the overall complexity, which is for each state the complexity times the number of states. And finally, the last DP term is the answer. If you have a certain problem that requires something, how to return the answer, what to call, with which state you begin, or where will you find inside the tabulation, inside the table, the answer. So let's consider this non-classical example, UVA 10943. How do you add? It's a very simple problem. Given a number n, how many ways can a k number, where k is given also, less than n add up to n? For example, n equal 20, k equal 2. You have 21 ways, which are way number 1, 0 plus 20, way number 2, 1 plus 19, etc. You have 21 in all ways. So this is the question. How many ways you can have where the numbers are between 0 and the constraints are that k and n are less than 100. So this is the example, and in math we solve this as a combination k minus 1 from n plus k minus 1. But there are overlapping problems and we can use dynamic programming. What is the state in this case? Of course, we have two numbers. Both of them will constitute the state. Both of them will constitute a unique state. So given a number n and k, a number k, the number of ways to make n using k numbers is distinct. So this constitutes a distinct state. The base case. For k equal 1, this is a base case. You have only one way to constitute the number n. This is a very easy base case. What is the general case? For k strictly greater than 1, you subtract x from n, and it will become the state n minus x and k minus 1, since you used x. This is one number. And this is one option. We have how many options? You can vary x from 0 to n, so this is n plus 1 options. So this is the complete search recurrence, the base case, and the general case, which is ways of nk equal summation from x equals 0 to n ways of n minus x k minus 1. So of course there are overlapping sub-problems. Let's consider n equals 3, k equals 4. You can have it the sum of the n equal 3 for x equals 0, and n will remain 3, and k will become 3, or n equal 2, k3, or n equal 1, k3, or n equal 0 because x will become 3 and k equal always 4 minus 1. So you can see in red the states that are reached from more than one previous state. So for sure here is an example of overlapping and DP will be very good. So let us summarize the DP terms. The constraints that they are between 1 and 100. The state is nk. The space, how many different distinct states we have, n times k. And the transition is when you have to calculate the state nk, you have to sum the states n minus x k minus 1 for all x varying between 0 and n. For each state, because you have a summation for x varying from 0 to n, so the complexity to solve a state is of the order of n. The overall complexity is this times this, which give us order of n to the power 2 times k. And the answer is given when you call ways of nk. So this is the answer. And you have an additional in the problem UVA 10943, an additional request that you don't have to print the result, but the result modulo 1 million. So you need only the last 6 digits. This is the top-down approach. You have the recursive function ways, which memoizes the states, and as usual, if you have already memoized it, you returned it, else you sum. You have the for each loop from 0 to n, and you sum always the you cumulate the number of ways of n minus split, where split vary between 0 and n, k minus 1, and you always calculate modulo 1 million. And finally, in the main you call ways of n minus k in order to get the answer. So memo is the memoization table. You set it to -1 and then you do all this. So this is easy. Another solution is the bottom-up solution. Why do we consider this version? Because this is the most natural. Because this table is a shared table. So the bottom-up approach will be more suitable to solve this kind of problem. You fill it once, since n and k vary between 0 and 100. You fill it once and you query it each time you need an answer. This is a natural way to do the things. So how do we fill it? Each column depends on the previous. So let's recall the equation. In order to solve n or n comma k, you need to sum all over k minus 1. So each column needs only the data that is in the column k minus 1, and this is for summing x or split or whatever varying from 0 to n. So this is a snapshot of the first 10 times 10 elements. You can see you calculate the column 0, the column the column 0 you don't calculate it, you don't need it, but it is -1. You calculate the column 1, and based on the column 1 you iterate several times to calculate the column 2, and so on. So this is the code for the bottom-up approach, and we solve it using 3 nested loops. First, to be correct in the topological order for each j, and then for each I, because as we saw, this is the formula. And then for each I, in order to know the value of each I, we said that you have to summate over split. So for each I, you make the summation. So GPIJ contributes in calculating the next GPI plus split JPEG plus 1. At each time you are at a given column, you can contribute in adding your value to the next columns because this is a formula. So this is the bottom-up approach, and next we will see the cutting sticks problem.